Let a1, a2, all the way to a of n are positive numbers. Then their arithmetic mean is greater than or equal to their geometric mean. This is so-called AMGM inequality. I'm going to give an interesting proof of the inequality. I'm going to change the numbers of a1, a2 to a of n, but keep their arithmetic mean fixed, and see how different combinations of the numbers affect their geometric mean. Let's first look at the simplest case of n equals 2. We are going to prove that a1 plus a2 divided by 2 is greater than or equal to the square root of a1 times a2. The left-hand side is the arithmetic mean. We define it to be m. We are going to prove that the square root of a1 times a2 is less than or equal to m. Squaring both sides, we need to prove a1 times a2 is less than or equal to m squared. Let a1 equals m minus d for some real number d. Then a2 should be m plus d, so that their average is m. D can be positive, negative, or zero. It is a measure of the distance from a1 and a2 to their average m. We have a1 times a2 equals m minus d times m plus d equals m squared minus d squared, which is less than or equal to m squared. We are done. Easy enough? Of course. But if we take a closer look, this simple proof actually tells us more details. Keep m fixed. The larger for d in absolute value, the smaller of the product of a1 and a2. A quick summary of the observation. Assume a1, a2, b1, and b2 are 4 positive numbers, so that their average of a1 and a2 and the average of b1 and b2 are the same, which is C. Question: which is larger, a1 times a2 or b1 times b2? In the graph above, a1 and a2 has larger distance to their average. Therefore, a1 times a2 is relatively smaller. This can be used to prove the general case of n variables. That's the arithmetic mean of the n variables is m. We are going to prove that the product of the n variables is less than equal to m to the power n. It is trivial if all the n variables are the same. Otherwise, there must be at least 2 variables. One is less than m and the other is greater than m. Without loss of generality, we assume a of n minus 1 is less than m and a of n is greater than m. I'm going to compare the product of the n variables for different a of n minus 1 and a of n. I will keep the first n minus 2 variables unchanged. I will also keep a of n minus 1 plus a of n unchanged. Let a prime of n minus 1 be such that a of n minus 1 plus a of n equals a of n minus 1 prime plus m. In other words, I'm going to replace a of n minus 1 by a of n minus 1 prime and replacing A of n by m. We will prove that A of n minus 1 times an is less than A of n minus 1 prime times m. Look at the graph. an minus 1 is less than m, and A of n is larger. We assume their average is C. Then C is the midpoint of the segment A of n minus 1 and A of n. Therefore, C is also the midpoint of the segment M and A of n minus 1 prime. Of course, A of n minus 1 times A of n is less than A of n minus 1 prime times M. By replacing A of n minus 1 and A of n with two new variables, A of n minus 1 prime and M, we have another n positive numbers. The first n minus 2 number unchanged and replace another two numbers. The sum is still the same, but one of them is M. So the first n minus 1 numbers have a sum n minus 1 times m. In other words, the average of the n minus 1 number is m. On the other hand, let's look at their product. After the replacement, we have a larger product. Our goal is to prove that the original product of the n number is less than or equal to m to the power n. We are done if we can prove the larger product a1, a2 all the way to n minus 1 prime times m is less than or equal to m to the power n. One of them is m, remove it from both sides. We need to prove that the product of the n minus 1 numbers is less than or equal to m to the power n minus 1. Now, let's see what we have. We have n minus 1 numbers. Their average is m, and we want to prove that their product is less than or equal to m to the power n minus 1. So we successfully reduce the problem of n variable to n minus 1 variable. We can repeat this process again and again to n minus 2 variables, n minus 3 variables, all the way down to 2 variables, which we already established. Therefore, we can prove this inequality by the principle of mathematical induction. An exercise. Let a1, a2, a3, a4 are positive numbers between 1 and 10, and their average is 4. We need to prove that the product of the 4 numbers is between 40 and 256. The upper bound, 256, can be established by the AM-GM inequality we discussed today. The interesting part is the lower bound, 40. It can also be established by the technique we discussed today. Thank you for watching the video. Please consider subscription of my channel. I appreciate your support.